Okay, so this next sequence of videos is going to illustrate how to solve an RC or RL circuit, or really any circuit with any number of passive elements in them, and they could be resistors, inductors, or capacitors, with sinusoidal input functions. So the first way we're going to solve this is with what we know so far, and that's how do we analyze this in what's called time domain. That's the domain where time is the variable. Okay, so if we have this basic circuit, it's a single loop circuit consisting of a voltage source that has value Vm cosine omega t, a resistor, and an inductor. Let's find I as a function of time in this circuit. Since it's a single loop circuit, all we need is a KVL to solve it, so that would be the voltage Vs. It must equal summation of VR across the resistor and VL across the inductor. Okay. Regardless of the analysis technique we use, this will always be true. So subbing in our IV relationships and anything that we know, we get Vm cosine equals R times I plus L di over dt. So this is a differential equation. This is a first order differential equation because we have a di and the I as terms inside the equation. In general, each one of these, what I call reactive elements, and you're going to know why it's called a reactive element in a couple of these videos. Each one of these will result in increasing the order of our differential equation, because this di term showed up because of the inductor. Okay, so you can see right away that this differential equation, a first order differential equation describing the V and the I, the flow of the current in a very basic circuit with only a couple elements. Okay. So to solve this, I'm going to solve the differential equation firstly just by expecting a solution. My expected solution is going to take the form of the summation of a cosine and a sine. And the way I get to that is firstly by looking at what happens to this solution when the di over dt term equals 0, which it will at some point. And if that term goes to 0, I see that I is going to look like some kind of cosine. But also when the term with the I as a function of time goes to 0, di dt is going to look like a cosine. Therefore, I is going to have the form of sine. So I know that there are going to be those two pieces to my solution, so I can sum them together. And then I'm going to have some kind of constants out in front that I'm going to have to figure out what those are. Coefficients, rather, out in front of the cosine and the sine. So given that this is my expected form of the solution, I'm going to substitute that into my original KVL equation up here. And this is what I get. Looks a little bit messy. So we take that and let's do a little bit of simplification, moving everything over to one side of the axis, so we'll be at a group terms, and I get Ri1 cosine plus Li2 cosine minus Vm cosine plus Ri2 sine minus Li1 sine. Alright, so now grouping the cosine and the sine terms, I get this expression shown here. So I see that I get cosine times some algebraic relationship plus sine times some algebraic relationship. And noting that the only possible way that this equation is true, in other words, the cosine and the sine summed together are going to equal to 0, is if the arguments in front of the cosine and the sine are also equal to 0. So I have an equation now, Ri1 plus omega Li2 minus Vm equals 0, and Ri2 minus omega Li1 equal to 0. I have two equations, two unknowns, I1 and I2. Solve this, and I get these solutions. So now I can take these two solutions for my coefficients I1 and I2 and sub them back into my expected form of the solution, and this is what I get. I as a function of time equals RVM over R squared plus omega squared L squared cosine plus omega L Vm over R squared plus omega squared L squared sine. Okay, so we're going to talk about this solution more in a minute, but let's make a couple of notes about it. Firstly, we see that we had a sinusoidal input function, and we get a sinusoidal output. Okay, it's a more complicated looking sinusoidal output, but it's a sinusoidal output. The amplitude of the sinusoid, well, we see that there's a summation. We're going to deal with that summation in a moment. Depends on the passive element parameters, R and L, as well as the amplitude of our input, which makes sense. But it also depends on omega, which is the frequency that we operate. This is interesting. Okay, it shows up in a few different ways. Note that if there wasn't an inductor, in other words, we operate this at DC as well, and we look at the argument in front of this cosine, we would end up with, let's just write this, if omega equals 0 or L equals 0, this would result in I equal R Vm over R squared cosine omega t, and the second term would go away completely, which would simplify to Vm over R cosine omega t amps. This simply looks like Ohm's law, I equals V, which is Vm cosine omega t over R resistance. Okay. So getting rid of the inductor, this obeys Ohm's law just like we would expect. So the inductor is what's kind of causing the complexity here. So one way to simplify this is we can actually combine the cosine and the sine. Recall from the last video that they are essentially the same function. One is just a 90-degree phase shift from the other. So let's explore how to do that. I'm going to combine them just using vector mathematics, noting that I1 can be represented, or the first term can be represented by a vector with magnitude I1 and a phase angle of 0, denoting the cosine of signal. The second term can be represented by a vector in purple here with magnitude I2 and a phase shift of negative 90 degrees, in other words, the sine. Okay, so the summation of these two is going to be this vector in green, which is going to be magnitude Im, which is given our geometric relationships would be the square root of I1 squared plus I2 squared, which equals Vm over the square root of R squared plus omega squared L squared. And the angle is going to be the arctan of the B, which is I2 over A, which is I1. And since we're in quadrant 4, that will be negative. Recall complex numbers and conversion from rectangular to polar coordinates. So that would simplify to the negative of the arctan of omega L over R. So therefore, we can rewrite I as being the magnitude of that we just found times cosine omega t plus this phase shift that we just found. So simplify to Vm over the square root of R squared plus omega squared L squared times cosine omega t minus the arctan of omega L over R. So we had a cosine forcing function. That was our voltage source. Going through a series RL combination, and the output current is a cosine that is phase shifted, but just a cosine output, and with a magnitude that depends on the passive elements, our amplitude, and our frequency of operation. Okay, so we can do this, right? We use differential equations to solve the system. Even though there was only two passive elements, this was fairly complicated, but we can do it. And but it will get exponentially more complicated the more elements we have in there. So what we need to do is find out is there a better way to do this? Is there a better way to solve this kind of system?